In principle, anytime you have two devices communicating digitally, what this means is that there is some common memory area where both devices can read and write. In the particular case of the CPU communicating with I/O devices, what's always going on at a base level is that within that I/O device there's a small number of registers, and the CPU is connected directly to those registers such that it can read and write them. So when a device wants to send a message to the CPU, it writes data into its registers, which it expects the CPU to read, and when the CPU wants to communicate with the device, it writes something in the device's registers, which it expects the device to read. Note though that this arrangement is one-sided. The CPU can read and write the registers in the device, but the device cannot do the same with the registers in the CPU. Now the question becomes, how do we instruct the CPU to talk to these registers in the I/O devices? Well, there are two basic approaches. Some systems have what is called port-mapped I/O, whereas others have what is called memory-mapped I/O. In a port-mapped system, each individual register of the I/O devices is seen to the CPU as what's called a port, and each port has a number, much like every byte of memory has a number. To read and write to these ports, the CPU has specific instructions, usually called output and input. So say a CPU might expect an instruction that says something like, output the content of register 2 to port 4498, and this would copy the content of register 2 to whichever register on whichever device is mapped to port 4498. In a memory-mapped system, the idea is that some memory addresses, the sort of addresses that usually point to bytes in the system memory, are actually mapped to the registers of I/O devices rather than to memory. So say the instruction that copies register 5 to address 662C1A32, well, if that address is mapped to a register on an I/O device rather than to a byte of memory, then this instruction is not copying out to memory, it's actually doing output to that device. To make this distinction between port-mapped and memory-mapped clear, consider a system where every address is specified in 32 bits. Well, when you have 32 bits, that's 2 to the 32nd different possible values, which is about 4 billion something. So with 32-bit addresses, we have 4 billion something different unique addresses. So at the very most, the system can address 4 bytes of RAM, but usually a system doesn't have as much RAM as it can address. So most commonly, only a portion of all of the available memory addresses actually are mapped to bytes of RAM. In a system with port-mapped I/O, the ports are effectively a totally separate set of addresses. In a system with memory-mapped I/O, in contrast, we just have the regular memory addresses, and some portion of those addresses are actually mapped to the registers of the I/O devices. So here, for example, the addresses 000000 up to 0000FFFF, that range of addresses is mapped to the registers of the I/O devices. The addresses left over to actually get mapped to RAM then are the addresses from 00010000 all up to FFFFFFF. And more likely than not, that's still more addresses than we have bytes of RAM in our system. So still again, you most likely have left over some memory addresses which don't get mapped to anything at all. So you're probably wondering about the relative merits of port-mapped I/O versus memory-mapped I/O. Well, port-mapped I/O especially makes sense on systems where you don't have very many addresses. Say on a system with 16-bit addresses, 2 to the 16th is only 65,536, and that gives us a very small amount of memory to work with. And if some of those addresses were diverted away from memory and towards I/O devices, that would make things even worse. We'd have even fewer bytes of memory to work with. Most recent systems, however, don't use 16-bit addresses. They use at least 32, or sometimes now 64 bits. And 2 to the 64th especially is a really big number, so that gives us a huge range of addresses, far more than we'll ever probably have enough RAM for. So once your addresses get that big, if a handful of them are mapped to I/O devices, you would hardly notice. We'd still be left with far more addresses than we can really use. Primarily for this reason, most modern systems use memory-mapped I/O. However, there are exceptions, like say the Intel processors, mainly for historical reasons, actually use both a mix of port-mapped I/O and memory-mapped I/O. This is just one more way in which the whole x86 platform is a huge mess. Now, it often happens that an I/O device wants the CPU to look at its registers and do something. And so the question is, how does the device get the CPU to do this? Well, the simplest solution is that the device simply doesn't, and rather just expects the CPU to constantly, at a regular interval, check one or more registers of the device to see if the device wants the CPU to do anything. This strategy is called polling, and the obvious downside here is that it means the CPU ends up doing a lot of busy work, and it's especially inefficient for a device which only needs attention at irregular intervals. So while sometimes polling works just fine, there are quite a number of cases where it doesn't. So many devices use an alternative arrangement with what's called an interrupt line. An interrupt line simply is a line running from the device to the CPU over which the device can send an interrupt signal. The idea is that when the CPU receives an interrupt signal, it should drop whatever it's doing, go execute some designated piece of code, and then when done with that piece of code, resume execution of whatever it was doing. And the way this works is that when the CPU receives the interrupt line, it first needs to save the state of whatever code it is executing. So most importantly, we need to save the content of the program counter register, the register which holds the address of the next instruction, because when the interrupt has completed executing, we want to go back to whatever it is the CPU was doing. So we save that register and possibly some other registers, and very often say we'll put them on the stack of the currently executing program. And then once that is done, the CPU will jump to the address which corresponds to the interrupt number in the interrupt table. The interrupt table is simply a list of addresses somewhere in memory, and usually the CPU knows how to find that interrupt table because it has a special register which stores its address. So for example, when the CPU receives an interrupt from interrupt line 3, it goes and looks in the interrupt table to find the address for interrupt 3. So here say that's A2220010. So the CPU then jumps execution to that address, and that code runs, and when it's done running, the last thing that code does is send execution back to whatever was executing before the interrupt came in. So again, the whole idea here is that you want an I/O device to be able to tap the CPU on the shoulder, have the CPU drop whatever it is doing, and execute a particular piece of code that that device wants the CPU to execute. And so what we do is that typically at system startup, we set up this interrupt table so that it has addresses that correspond to the right interrupt lines for the right devices, and the code at those addresses should do whatever is appropriate to handle the interrupts coming in from the corresponding devices. A similar kind of mechanism is what's called hardware exceptions, or sometimes CPU exceptions. A hardware exception occurs when the CPU detects some undesirable state of affairs in its course of execution. Like say one classic example is if a CPU detects it's about to do a division operation where the denominator is 0, well, that's an improper kind of division, so most CPUs in that case will throw an exception. And when that happens, the CPU drops whatever it's doing, and it goes and looks in this special table, usually called the exception table, and it finds the address that corresponds to the number of the exception that occurred. Like say, if a divide by 0 triggers exception 2, then it looks and finds the address 82879594 here, and then the CPU then jumps execution to that address. And the idea was that the exception table was set up beforehand, presumably at system startup, and the code at that address somehow intelligently copes with the problem that occurred, the exception that occurred. In this particular case, a divide by 0 is really not something you want to happen at all, and so if it is attempted, probably what should happen is the program should basically terminate, and the user should be alerted of the issue.